So, this is Lab 3 on black hole orbits. The goal of this lab was to take our positions of our star over a given period of time, use basic physics principles such as Newton's second law and BPython to find the mass of the black hole. And of course, as a result, we ended up with our mass of the black hole being approximately 2.97 times 10 to the 31st kilograms, approximately 10 times larger than our original star mass. So, the overall layout for this presentation is going to be first, a discussion of the physics principles behind it, second, a discussion of how those physics principles can be used in a computer model form, and third, a discussion of the what if and what does it mean questions at the end. So, for the physics, we have our positions of our star, R1, R2, R3, so on. We have those to start with. Then, we can take those, take the difference, divided by the change of time, to get our velocities for each consecutive pair of positions. Of course, we can take each consecutive pair of velocities, take the difference, and get our changes in velocities, delta v. Those are helpful when we multiply them by the mass to get the change in momentum, and plug into Newton's second law, because we know the net force, which is going to be the force of gravity on the star due to the black hole, is equal to the derivative of momentum in relation to time, which we can approximate by delta p over delta t. Being now we have delta p and delta t, which gives us our force of gravity, which we can now use the gravitational force equation, and we can plug in our force of gravity, which is our net force, because we are assuming the only force acting on our system, i.e. star, is the force of gravity due to the black hole. And we also know big G, the m1, which we can say is the mass of our star, and the distance between the two, and solve for m2. So, how do we move that into code form? We start with plugging in our basic variables, our mass of our star, our change in time, our starting time of 0, and we read in all of our data from our given data sheet. We now have to calculate the velocities, which we do by creating two arrays for the x and y velocities. We take the difference in the x positions and the difference in the y positions, divide them by the change in time, and store them in our array. And we, at the end of the loop, increase the index, and after the loop is over, we reset the index to 1, and the time to the change in time, because we are starting at position 1 at the beginning of our next calculation loop. So, for our calculation loop, we have our v initial and v final, which we get by creating a vector from a pair of x and y velocities from our two previous arrays we just created. We now calculate the initial and final momentum by multiplying by mass, which is equivalent to what we did in our physics discussion, the second to last step, but we do here earlier on. But it's the same either way, because it carries through until the end here as well. So we calculate delta p, the difference in the two, and divide by delta t to get our approximation of our derivative at that specific point. Then, thanks to Newton's second law, we set our net force equal to that, and now we have to move on to calculating the parallel and perpendicular components of that. The parallel component is going to be in the direction of the initial momentum, because it's only a change in speed and not a curving, and it's going to be the difference in the magnitude of the two momentums times that unit vector in the original direction. And of course, thanks to Newton's second law, again, we have the net force in the parallel is also equal to the net force the net force in the parallel is also equal to the change in momentum in the parallel. And now we can calculate the perpendicular by subtracting the parallel from the whole, and of course set the net force in the perpendicular to the change in momentum in the perpendicular, once again thanks to Newton's second law. Now we can see a quick run of the thing here. Well, we'll have our black arrow, which comes up here, as our parallel force vector, and our blue arrow being our perpendicular force vector, and our yellow arrow being our total net force vector towards the black hole from the sun. So now we move on to our discussion of our what if and what does it mean questions. So, what does it mean? Discuss how the net force and change in momentum vectors are different. The net force vector is what causes the change in momentum, i.e. it's the source of the change in momentum. Otherwise, now, they are two independent concepts. However, they are connected by Newton's second law, or the momentum principle, i.e., we know they're equivalent due to that principle. However, if we did not know Newton's second law, all we would know is there are two separate concepts: the net force, which is just what's acting on the system, and the change of momentum, which is the change in the system's momentum. Now, the only way they're connected is by Newton's second law. We can find the change of momentum from, say, the positions like we did in the lab. However, we cannot find the net force without Newton's second law. So, now, what if we had a second black hole, which we swamped the first black hole, but we had the same positions from the two? Would we be able to tell any difference between those two black holes from the procedure we had? The answer is no, we would not, due to the fact that the only way we can determine anything about the black hole is through those positions, and if those positions are the same for the two black holes, then all we know is the masses are the same, and thus they are the same.